MI Drilling Fluids Company's engineering research laboratory, located in Houston, Texas, conducts drilling engineering research and develops innovative mud testing equipment. We use the medium of video to broaden the industry's knowledge of hole cleaning in high angle and horizontal wells. We have developed several specialized flow loops, two of which are shown here, to study cuttings transport in angled holes. The ERD flow loop has a straight 15-foot long, 4-inch diameter test section made of cast acrylic tubing. The 1.9-inch diameter drill string, seen in front of the ERD loop, can be placed either centered or eccentrically and can be rotated up to 150 RPM. The test section angle can be varied from 90 to 35 degrees from vertical. The variable geometry flow loop is used to compare different intervals in the same well. The adaptability of this test section allows configuration simulating most well bores. The mud pit provides a normal circulating volume of 1.5 barrels. Flow rates of up to 125 gallons per minute are measured with a mass flow meter. Here we see a low solids non-dispersed fluid at 80 degrees flowing at 200 feet per minute without rotation. Notice that although a bed is formed, it does not slide because the hole angle is close to horizontal. The particle transport mechanism here is saltation flow along the top of the bed. Here, a lightly dispersed mud is flowing at 200 feet per minute at a 35-degree angle. Notice the avalanching when the pump is shut off. This demonstrates why the angles between 30 and 60 degrees are the most difficult to clean. This close-up of our ZAG tube clearly shows the slower, hindered settling typical of vertical intervals. The rapid boycott settling, shown at 45 degrees, illustrates the clarified layer along the upper side and the slump along the lower side of the tube. Boycott settling causes some particles to move upward with the flow stream. Others are momentarily suspended, while still others form a bed along the bottom of the hole and slump opposite to the direction of flow. Water in turbulent flow at 200 feet per minute in a fully eccentric horizontal annulus can efficiently clean the hole. The same water at 45 degrees, also in a fully eccentric annulus, does not clean this interval at the same annular velocity. The net movement of the solids in this case is downward, opposite to the direction of flow. The total collapse of the bed caused the solids to pack off and completely plug the annulus when the pump was stopped. These vortices, seen now in slow motion, greatly hinder good hole cleaning and amply demonstrate that efficient cleaning in one hole interval, the horizontal as was seen in the last segment, does not guarantee good hole cleaning in another interval of the same well. Abrupt hole geometry changes create low-energy areas that allow cuttings to build up. These changes include changes in angle as well as in hole diameter. The abrupt annular velocity decrease in washed-out intervals allows additional bed deposition and cuttings recirculation. Dune transport, a form of saltation flow, is a typical transport mechanism. While this results in the movement of a large number of cuttings up the hole, it does not provide efficient hole cleaning. Rotation of the drill string will break up the dunes, increase the cutting's concentration in the flow stream, and reduce the bed thickness. Fluids that provide viscosity at high shear rates but have little low shear rate support, such as this CMC slurry, will erode existing beds as the annular velocity is increased. However, note the inability of this fluid to support even the smallest of these sand particles when the pump is stopped. This type of fluid can give high yield points and still have minimal 6 and 3 fan viscometer values and gel strengths. This sequence compares the transport capability of a fluid with poor low shear rate viscosities, HEC on the left, with one with excellent low shear rate viscosities, the biopolymer, on the right. Note the helical flow pattern in the biopolymer fluid. The ability of the biopolymer to adequately suspend cuttings is also evident when flow stops. Note the continued slow rotation of the cuttings on the right as compared to the poor support and hopping motion of only a few particles on the left. The drill pipe is 80% eccentric and rotating at 150 RPM in both cases. Pipe eccentricity and the resulting skewed flow profiles have a dramatic effect on hole cleaning as shown in this MI computer simulation of slot flow. Such skewed profiles encourage bed formation because cuttings tend to migrate toward the low flow rate or low energy transfer regions of the annulus. In a slower look at this sequence, we take a centered pipe in a Newtonian fluid and make it progressively more eccentric until the eccentricity reaches 100%. Very high annular velocities may exist along the upper portion of the annulus, while little to no flow may occur around a highly eccentric, non-rotating drill pipe. Then, keeping the pipe fully eccentric, we make the fluid progressively less Newtonian. The more non-Newtonian a fluid becomes, the more it assumes a flat, plug-like flow profile. This results in an excellent transfer of energy to the suspended cuttings in the main body of the flow stream, and a correspondingly poor energy transfer around the eccentric, non-rotating drill pipe. The flow profile resulting from pipe eccentricity can clearly be seen here. Without rotation, more cuttings are transported in the 20% eccentric annulus on the left than in the 80% eccentric annulus on the right. The addition of rotational energy dramatically improves the transport capability in the 80% eccentric annulus. The biopolymer fluid continues to flow at 50 feet per minute. This segment shows the flow profile of a viscoelastic biopolymer in a pipe instead of an annulus. We can see the plug flow profile of this fluid as the camera moves parallel to the axis of the tube at the same speed as the fastest moving fluid. This plug zone fills most of the diameter of the tube, resulting in a low shear rate region in the center of the plug and high shear rate regions adjacent to the tube walls. Increasing the annular velocity does not greatly affect the plug profile of this fluid. The low shear region in the center of the plug is slightly reduced in size, while the high shear region along the walls is somewhat larger. Rotating an eccentric drill string in these biopolymer fluids improves hole cleaning due to the viscous coupling that exists between the rotating pipe and the fluid. This viscous coupling greatly improves the energy transfer to the cuttings, allowing the helical flow pattern seen here. The better the transfer of energy to the cuttings, the better the hole cleaning. This segment is taken from the validation test series of our SiSalt system before it was used as a drill-in fluid in near horizontal wells in West Africa. Its low shear support capability provides superior hole cleaning at typical annular velocities, even in a highly eccentric non-rotating annulus, and at high angle as well as intermediate angle intervals. Note the increasing bed thickness at 45 degrees as the flow rate is systematically decreased from 180 feet per minute to 0. Although it provides superior suspension at all flow rates and hole angles, it is unable to prevent bed formation at the lower flow rates. Note also that no bed slumping occurs until the pump has stopped. This slow bed slump occurs even though the cuttings in the flow stream are perfectly suspended. Viscous sweeps are generally ineffective at high angles unless the cuttings bed is simultaneously agitated by pipe movement and/or turbulent flow. In slow motion, we can see how the viscous sweep readily deforms and passes over the top of the cuttings bed. This sequence demonstrates the effectiveness of pipe rotation. Rotation is more effective at high eccentricities and when the fluid provides sufficient suspension and a good viscous coupling to carry the particles in a helical flow pattern. Rotation of a highly eccentric drill string aids cuttings transport even at intermediate angles such as the 55-degree angle seen here. We hope this presentation has given you sufficient background information to realize that drilling high-angle wells can be much more complex than drilling vertical wells, and that this knowledge will assist you in the successful completion of your next well.